Okay, so we're going to talk about the review for exam 3. First off, you got to know your vocabulary words. So you're going to find those on the handout. You can also look for them in the book. Typically, they're going to be at the beginning of the sections, but you also might find them in the middle of a section. They're going to be bolded, and make sure you understand what the words are and the circumstances around them. Okay, we've talked about this on the previous exams, reviews, so make sure you're prepared to answer questions on those. And then we're going to go over some examples of questions, types of questions you might see on the review. Recall that in your review you will have a key at the end, and that you need to make sure you submit not this one but your review for your quiz grade and also for the bonus on the test. Alright, so let's get started on these questions. So we've got we're going to use the theoretical method to determine the probability of the given outcome or event and state any assumptions that you need to make. Alright, so rolling a single 6-sided die and getting an even number. So we talked about dies throughout this section. So if we've got, we're looking at rolling an even, so that would be a 2, a 4, and a 6, right? So there's 3 outcomes. It doesn't matter what color they are this time, but we've got 3 possible outcomes out of how many total outcomes? Remember, on a die, there are 6 sides. So this will be exam 3 review, number 1A. We have 3 outcomes out of a total of 6 outcomes. And then we're going to reduce that down. 3 and 6 both divide by 3, so I end up with 1 over 2. All right. Let's look at part B. So part B says, drawing a 10 from a standard deck of 52 cards. So we've talked about, there are certain things you need to know. You need to know how many suits there are and what those are. So there's 4 suits with hearts, diamonds, clubs, and spades. And because of that, there are, and there's different cards, right? So there's 2 through 10 are number cards. You have the ace card. You have the Jack, Queen, King card. So for drawing a 10, that means there's a 10 of spades, a 10 of clubs, a 10 of hearts, and a 10 of diamonds. So there's 4 10s out of the total deck of 52. So this will be 4 10s out of 52 cards. They both will reduce by 4, and we end up with 1 out of 13. All right, let's look at C. Finding that when tossing a coin, it turns up tails, given that it has turned up tails in the previous 5 tosses. So those previous 5 tosses have nothing to do with it. Remember, when we are flipping a coin, we are, we always have the same possible outcome. The possible outcomes are tail and heads. So it's always still going to be 1 out of 2. Just like when having a child, there's a chance of a boy or a girl. So for this one, even though they've added all this other stuff, it's going to be 1 out of 2. All right, part D. What is the probability of randomly selecting a day of the week whose name doesn't include the letter D? All right, so we have Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. So there's 7 days in the week, and they all have the word or the letter D in them because they're all a day. So what's the probability of that? It's going to be 0 out of 7, which will get us to 0. Okay? All right. So that's, oops, and this should be example 2 because example 1 was the word. Sorry about that. All right, let's go on to number 3. So in each case, find the probability of the given event and state any assumptions that you use. I'm not necessarily looking for the assumptions. I'm looking more that you can do that. So not drawing a queen from a standard deck of 52 playing cards. So this is very similar to us drawing the 10, except it's the complement of it. Here we were drawing a 10. Remember there were 4 10s in a deck. There's going to be 4 6s, 4 kings, 4 queens, 4 jacks, 4 aces, 4 2s. There's 4 of each card in a deck. So, but this here we're looking at not drawing it. This was the complement. So, for part A, we are looking at P, not a queen. That's going to be equal to 1 minus P of drawing a queen. So the not a queen is equal to 1 minus that probability of gathering a queen. Or not gathering, but selecting a queen. And we know that the probability of drawing a queen was the same as the probability of drawing a 10. So this will be 1 minus 4 out of 52. And we've talked before, we need to change this to a common denominator. So 52 out of 52 minus 4 out of 52. This will get us 48 out of 52. They both divide by 4. 48 divided by 4 will get us 12. And 52 divided by 4 will get us 13. So there's a possibility 12 out of 13, or the probability is 12 out of 13 of not getting a queen. All right, part B. What is the probability of randomly selecting a person and getting someone who does not have typo blood, given that 45% of the people have typo blood? So this is the same type of situation. So we're looking at the probability of not type O will be equal to 1 minus the probability of type O. So 1 minus the probability of a typo, they said, was 45 out of 100. So if we're looking at that, and how do we know it's 45 over 100? Well, because they gave it at 45%. And I can change that to be a fraction of 45 out of 100%, right? So 45 out of 100. All right, so we need to get our common denominators again. So 100 over 100 minus 45 out of 100. Well, 100 minus 45 will get us 55. And again, our common denominators stay the same. We don't change those at all. And then this will reduce down. They both will divide by 5. So 55 divided by 5 will get us 11, and 100 divided by 5 will get us 20. All right, question 4. So for question 4, in terms of the law of large numbers, explain why you should not be surprised to see 7 heads in 10 tosses of a fair coin, but you should be surprised to see 700 heads in 1,000 tosses of the same coin. Well, the law of large numbers states that the larger the tosses, in this case, the tosses of the coin, the closer we should get to our expected value. In the small numbers, which is 10 tosses, it's okay that, and we should probably expect that we're not going to get 5 out of 10, right? The 1 out of 2 on flipping a coin is because we have 2 sides, right? So it's a 50-50 chance. But when we're only flipping 7 of those, or 10 of those coins, we don't expect to get 5 out of 10. But the more and more and more we toss our coins with 1,000 tosses, we should expect to see that it gets closer to 500 heads, not 700. Okay? So we would expect it closer to 500. All right, let's see if we can write some words there. So for 10 tosses, it's a small number. So we're probably likely to not get 5, right? Or 5 heads, we'll put it that way, so it's more clear. But with 1,000 tosses, this is a large number. So we are likely to get 500 heads. Or let's see, we'll put this more likely to get 500 heads with our tosses. Okay, because that's what typically we'll get closer to. So that means that that 700 is going to be highly improbable. Okay. All right, number 5. What is the gambler's fallacy? So if you recall, this was another example, right? What is the gambler's or vocabulary word? So the gambler's fallacy is the mistaken belief that a streak of bad luck makes a person due for a streak of good luck, or that the streak of good luck will continue. There's lots of examples for this, so let me put this in here. So gambler's fallacy is the mistaken belief that a streak of bad luck makes a person due for a streak of good luck. Or like the streak of good luck will continue. So let me put that in parentheses. Or a streak of good luck will continue. So there's many examples you can do for this. There are many, and they can vary slightly from what I'm going to use. But if let's say we flip a coin and it lands on heads 5 times, most people will believe that the coin will land on tails the next time. And this is because it's due for a change. So that's just one example you could use. There's many, but it's just understanding this concept of the gambler's fallacy. All right, let's go look at number 6. A job seeker, that's somebody who's looking for a job, sends their resume to a very large number of potential employers. What does it mean to say that the law of averages will have someone eventually hiring the job seeker? Is it true? And explain. All right, so example 6. So what they're saying is applying that law of large numbers is that the job seeker is due to be for being hired, right? So the job seeker is due for being hired, all right? So if being hired for jobs happens randomly, then the statement is not true. But if being hired for jobs depends on the resume submissions, it may be a true statement. Let's go read this example again. A job seeker sends their resume to a very large number of potential employers. What does it mean to say that the law of averages will have someone eventually hiring the job seeker? And is it true? And explain why. Well, what they're saying is that if the law of averages, which is the law of large numbers, remember we could be said two different ways, but it means the same thing. We'll have someone eventually hiring the job seeker. Well, if they send out a lot of job applications, the potential for being hired can increase because you have more people that you have sent it to. But it doesn't mean that that's the only reason why they're going to get a job, right? It depends on whether or not they're qualified for the jobs that they are sending in those resumes. So there's a little bit of added things you can look at with this one. All right, so let me write a little bit more of what I was saying earlier. So if being hired for jobs happens randomly, then the statement is not true. So if it's just random that you get a job, it won't be true because it has nothing to do with how many you send in. It's just a random thing, right? But if being hired for jobs depends on resume submissions, it may be true. Now, usually it depends on resume submissions, right? Because if you don't submit a resume, you can't get hired. But that's not the only thing there. You still have to be qualified. So that's where this is talking about, like, what does that mean? You know, if someone just submits a bunch of resumes, well, then they're due to be hired, right? Well, they're more likely to get hired. But it doesn't mean they will be. All right, we've got a roulette wheel. It has 38 numbers. 18 of them are odd. That's the black. And 18 are red, or the even, which are red. As well as a 0 and a double 0, which are green. If you bet $5 that the outcome is an odd number, the probability of losing the $5 is 20 to 38. So let's talk about why it's 20 out of 38. All right, so if you bet $5 that the outcome is odd, then your probability of winning is 18 out of the total. Well, how many total do we have? We have 18 plus 18, that's 36, plus a 0, that's 37, plus a double 0, that's 38. So winning would be the 18 out of the total of 38. But losing would be the 18 plus the 1 plus the 1, because those are not odd. So that makes that 18, 19, 20. So 20 out of 38. The probability of winning $10 for a net gain of only $5. So why is it there only a net gain of 5? Because you had to pay 5 to play. So you bet 5, but the outcome is odd. You've already paid that. And then you gain $5, so you now have 10, but 5 of that was because you already paid 5. So that outcome is 18 out of 38. So if you bet 5 that the outcome is an odd number, what is your expected value? All right. So for the expected value for this, we bet $5. So our expected value will be equal to the negative of $5 times the 20 out of 38 plus $5 times our 18 out of 36. Because it's a negative for the loss of 20 out of 38 and then positive for the win of 18 out of 38 if it's odd. And we can do this. These are kind of bigger numbers, so we could do this as a whole thing into the calculator, or you can separate it and then add them. I just put it in the calculator and I got a negative 0.26. So just so you understand, that's a negative $0.26, so that's a loss of 26 cents. So which of these options is best? Should we bet on odd or don't bet, and why? Well, if we're just looking at what the outcome is, the outcome is that you're going to lose 26 cents for the expected value of it. So for this case, the best option is not to bet, because the expected value for no bet is 0 instead of the expected value for betting is losing 26 cents. Okay? So if you don't bet, you don't lose anything, but the expected value for betting, you're going to lose money. So in this case, it would be don't bet. All right, number 8. A pollster, someone who's taking a poll, randomly selects an adult for a survey. Let M denote the event of getting a male, and let R denote the event of getting a Republican. Are events M and R overlapping? So they're taking a survey, and they're looking at some males, and they're looking at Republicans. Can you get an overlapping event of a male Republican? Well, yes. A pollster could select an adult who is a male Republican. So they could occur at the same time, so those events could be overlapping. All right. Number 9. Number 9, assume that boys and girls are equally likely and the gender of a child is independent of the gender of any brothers or sisters. If a couple already has 3 girls, find the probability of getting a girl when the 4th baby is born. So this is similar to what we did in problem 1C, where we saw that it has already turned up tails in the previous 5 tosses. This part didn't matter, right? Tossing a coin is still 1 out of 2. And I mentioned then that having a baby is still 1 out of 2. Is it a boy or a girl? So just because they already have 3 girls, the probability of getting a girl on the 4th baby is still going to be 1 out of 2. It doesn't matter how many times you've had a girl or a boy. We're just looking at the independent event of having a baby. Still a chance, boy or girl. All right, number 10. So for number 10, 50 songs on a smartphone consist of 15 that are rock, 20 that are jazz, 15 that are country, and the selections are played randomly and can be repeated. What is the probability of each of the following events? The first 2 selections are both rock. All right, so we're looking at the probability of getting 2 rock songs in a row, because it says the first 2, right? Getting 2 in a row. So the probability, we have to first find out, we've got a total of 50, right? 50 songs. 15 are rock, 20 are jazz, and 15 are country. So we've got to look at the probability of getting a rock song. That's 15 out of 50. So this will be equal to 15 out of 50 for the first event. And then we will multiply that times 15 out of 50 for the second event. Put that in your calculator, we get 0.09. All right, let's go look at B. So part B says the first 3 selections are all jazz. Well, jazz has 20 out of 50. So the probability of 3 jazz selections in a row will be equal to 20 out of 50 times 20 out of 50 times 20 out of 50. So you don't have to put the multiplication sign. You can just put the parentheses next to each other. If we put that in a calculator, we get 0.064. All right, let's go look at C. For C, it says the first selection is jazz, and then the second is country. So this is the probability of jazz, then country. So the probability for country is 15 out of 50. So this will be equal to the jazz of 20 over 50 times the country, which is 15 out of 50. And if we multiply that in our calculator, we will get 0.12. Now part D says the second selection is the same song as the first. So what's the probability of getting one song and then getting that same exact song for the second song? Well, each of the 50 songs are available for each selection, right? No matter which song is played first, the probability for each consecutive song is the same. So we're looking at one song out of a total of 50. So for part D, it will be 1 out of 50, which is 0.2 if we're looking for decimals. Okay? So 1 out of 50. Or you could, because the others, we took it to decimal places, you could do 0.2. Either one. So each song has that same probability of being played. There's 50 songs, 1 out of 50 chance. All right, number 11. In a clinical trial of an allergy medication, 110 people are treated with the medication and 101 other people are given a placebo. A control group consists of 79 people who are given neither the medication nor the placebo. The number of people in each group who showed improvement appears in the table below. So we have improvement, we have no improvement. This is the allergy drug, this is the placebo, this is the control group. So our total is 290 either way. So we're going to answer some questions off of this. The first one is, what is the probability that a randomly selected person in the study was given either the drug or the placebo? So the ors, remember, are a union, right? We have the different types of probabilities. We have where it has to be in this and that. That's where they overlap, so that's an intersection. But in this case, because it's the or, it could be this group or that group. So randomly selected person in the study was given either the drug or the placebo. Well, the total people for the drug are 110, and the total people for the placebo are 101. So, let's see if we can kind of keep that into play so you can kind of see what we're looking at. All right, so this is 11 part A. So we're looking at combining those together, right? So we have 110 for the drug, plus we have 101 on the placebo out of a total still of 290. And you could write these as two separate fractions if you want to, but we're adding them together out of the whole total. On the top, we will get 211 over 290, and then we can take that down to a decimal of 0.728 by putting it in our calculator. All right, part B. What is the probability that a randomly selected person either improved or did not improve? All right, so let me come up here for just a second. So let me clarify what this was. This is the probability of drug or placebo. Okay? This will be the probability of improved or not improved. So the improved, there were 137 that improved, and there were 153 that did not improve. Still out of our total of 290. Well, on the top, when we add that, we get 290 out of 290, which is equal to 1. Does that make sense to you? Well, if we're looking at the whole purpose of this experiment, this clinical trial, is to see who improves and doesn't improve. So everybody has to either improve or not improve. And that's why it's going to be a 1, because everybody is going to be in that case. All right, part C. What is the probability that a randomly selected person either was given the drug or they were improved? So this will be the probability of the drug or improved. So this is another union situation here, but in this case, it's a little bit different. Before, we had improved, non-improved, or we had drug and placebo. There was no intersection. There was no overlap for this. In this case, if we're looking at getting the drug and improving, there is an overlap that happens of 60 because we're using this column, the allergy drug, and this column of the improved. So at this point where they would intersect, we have to not count that twice. So the first thing I'm going to show you is there's a formula for that, right? We can do the probability equals the probability of the drug plus the probability of improved minus the probability of drug and improved, where they overlap. So this, if we do it this way, would be equal to the drug was 110 out of 290. Improved was 137, going this way, 137 out of 290. But where they overlapped would be 60 over 290. Well, if we work it this way, on the top we have 110 plus 137 minus 60. So that would get us 247 minus 60 will get us 187 over 290, which gets us 0.645. All right? Now, there's also another way you could look at it if you want to do it this way. It's still the probability of the drug or improved. And what you can do is just add up the numbers and include everything that the improved and then this. So you could add the separate numbers. So 60, I'll go across for improved first, 45, 32, and the 50, that's still the other number in the drug. And you can put that all over 290. Either one is mathematically okay. You're still going to get, when you add these up, you'll still get 187 out of 290, which will still get you the same answer. Either one is mathematically correct. This is more of what we've been doing as far as our work, but you could add all the improvements plus the 50. Okay? You just can't do the 60 twice. That's the big key. Can't do the overlap. All right, the last question is, what is the probability that a randomly selected person was given the drug and improved? So that means we're talking about those who got the drug and they improved. The only one that's happening there is going to be the 60. They improved and they got the drug. That's the intersection part. So the probability of the drug and improved will be 60 out of 290, which will be 0.21. All right, and if you're like, but which one will be okay for the test on the part C? Either way, as long as you're showing your work and I can understand what you're doing. All right, number 12. For each pair, state whether you believe that there is a correlation between the two variables. And if you believe there is, state whether it is positive or negative and explain some reasoning. All right, we're on to number 12, part A. The weights of taxicab passengers and the cost of their trip. So not the weight of the taxicab, but the actual passengers. Does the weight of the passengers affect the cost of the trips? Well, I would say no. Now, the weight of the taxi could, right? Because the price of gas might be a little bit different, but no. The weight of the passengers has nothing to do with it. Because we're not talking about gas mileage either. We're just talking about the cost of trip, which is typically already predetermined before the passengers get in there. So they're uncorrelated. And that's because the weight of the taxicab person, or the weight of passengers does not affect the cost of the ride. Okay? They don't decide, oh, well, you're this size, so I'm going to charge less or I'm going to charge more. It's all the same. All right, part B. The pulse rate in beats per minute and SAT scores of adults. Well, these are the results. Again, it's not in the process of taking the exam, but just the result. These are not correlated either. So uncorrelated. So the pulse rate does not affect the score. Of the SATs. Okay. Depending on what their pulse rate is, doesn't mean it's going to change the score when they're looking at their scores. And part C, the weights of gasoline-powered cars and the distances they can travel on a gallon of gas. All right, so I mentioned this a minute ago. So the weight of the car and the gasoline. So does that have a correlation? Well, this one is correlated. And let's talk about that. As the weight goes up, what happens to the gas mileage? The MPG, the miles per gallon, goes down. The more the car weighs, the lower the gas mileage will be. So this will have a negative correlation. All right, number 13. We're looking at a graph here, and on the graph we've got an outlier out here. So it says, which point is an outlier? Well, we can find the point by going up. This would be 0.4, and over would be 1. So the point is 0.4, 1.0. And it says, ignoring the outlier, estimate or compute the correlation coefficient for the remaining points. So if I take this point out, because it's a, what would we expect the correlation to be? Well, if I take this one out, all I have is this group of dots, right? There's no correlation there. So the correlation would be 0, because it's just a blob. It's not linear. So excluding the outlier, the correlation would be 0. Because there's no linear process to that. Now, if we include the outlier, how does the outlier affect the correlation coefficient? So we can estimate, we could compute it if we wanted to pull all the points out, but I'm not going to do that. We could, if we wanted to include it, what does it look like here? if we include that outlier, then there's a negative correlation. It's going down, but it would be linear with that. It's not going to be a very strong one. So we could say that for part B, including the outlier, it would be a weak negative correlation. Okay? Because it will come down, but it's not strong because there's not much else up here. There would be like 3 dots that hit on the line, but it's still not going to be a strong one. All right, so those are the types of things you need to know how to do for the exam. You might be wondering, like, but you didn't have to find the coefficient, because I don't know that everybody's going to have access to a TI-8384 calculator in order to find the coefficient, but you're going to need to be able to tell me about the correlation. All right, and I know you've had practice finding the correlation using your calculators or the Desmos.com site in the activity and in your homework. All right, so make sure you study and know what's on this exam, that you can figure out how to do all the problems so that you can have a good exam grade.